Live from the BBC, The Naked Scientists.
And a very good evening to you in radio land and podcast land out there. We are The Naked Scientists. It's me, Dr. Kat Arney, and here with me is Dr. Dave Ansell.
Hi, and we're going to be telling you why gossip may actually be a good thing for you and how scientists want to use lasers to push satellites around.
And also joining us in the studio, we have the ever-wonderful Mandy Morton.
Good evening.
Who is working the desk tonight because Chris, we have chopped into small pieces and buried in the cellar. No, Chris is at a conference over in the States, I believe. So he'll be joining us with some reports later, so he can't completely stay out of it. But also in the studio, we have two very special guests. We have Jez Wells.
Hello.
And we have Hugh Hunt.
Hello.
And they're here to discuss aspects that are very close to my heart of music and music technology. How do we hear different sounds? How are different sounds made? And how can we recreate all sorts of sounds that we thought we'd never hear again? So we're going to be having a very auditory show tonight. We want your questions. If you've got any questions about the technology of music, how sounds are made, what sort of things sound's being used for, get calling in 08459 25 2000, and you can email us at chris@thenakedscientist.com. So get calling in any questions to do with music, technology, and also general science and technology. Get calling in 08459 25 2000. And here we also have some news from Dave.
Well, scientists, astronomers have always had a big problem. They want to be able to see very, very small things a very long way away. And to do that, you need a really big telescope. But it works a lot better if you can get it in space, so you haven't got all that atmosphere to get in the way. So recently they've discovered a way of doing this. If you have lots of small telescopes, all flying in an array, you can build up, it's the same as having a really big telescope. So, but the problem is you've got to keep these satellites within sort of maybe about the size of 10 atoms. It's got to be incredibly accurate. So some researchers in America have come up with a way of doing this. What you do, instead of building a big heavy structure to hold it together, you use a big long piece of string and then you use a laser to push the satellites apart, because when light bounces off a mirror, it applies a force and it pushes them apart. And doing this, they reckon they can keep the satellites within 1 nanometre over a length of a kilometre.
So there's satellites, loads of little things all tied together with string in space.
Well, they want to. They haven't built it
being
yet.
kept in place by lasers.
Yes.
Wow. That's pretty impressive. More down-to-earth news from me is I'm a terrible gossip. I was out last night with my favourite girly friend, and boy, did we get stuck into some people. And this is actually apparently a good thing. Some researchers at the University of Oklahoma, led by Jennifer Bosson, have found that gossip actually creates friendships rather than breaking them. Because people who have something to gossip about a third party, another person that they dislike, it actually brings them closer together than talking about
They've got something in common.
Yeah, so your shared hatred of someone actually does work to build stronger friendships. A very interesting piece of research there about personal relationships. So yes, gossip, it's good for you apparently.
Now, David Gubbins at Leeds University, he's had a problem. He wants to know how the Earth's magnetic field has changed over the last 400 or 500 years, so we know what's happening to it. Problem is, no one measured it beyond like 150 years ago, so what do you do? He's worked out that in old ships' logs, not piece of wood, the things which they write down where they've been.
The captain's log.
The captain's log, that's the one, yeah.
Star date.
Sea date.
Sea date.
Yeah. Anyway, what they do is they wrote down the difference between magnetic north and grid north. And by putting all this data into a big computer, he's worked out how the Earth's magnetic field's changed over the last 400 or 500 years.
Ah.
And he's discovered that it was about stable until 1840, and it suddenly stopped dropping. It started dropping since then.
Well, what does this mean? Because is the Earth's magnetic field going to flip round? This is something that occupies my nightmares.
I'm glad. It actually ties in quite nicely with a question we've had from Chris, who lives in Kentucky. He wants to know how a flip, because the Earth's magnetic field occasionally flips, how this would affect technology and how long it would take. Now, the Earth's magnetic field, we don't really understand it. We think it's produced by something to do with lots of molten iron flowing around in the Earth's core. It's really difficult to model. Okay. And it seems to reverse on average, every 250,000 years. But it's been 1 million years since the last one flipped. So we think we're probably about due for one.
This is why I'm worried, you see.
I hope it's not going to be like buses.
Suddenly it will just go. There'll be 3 at once.
And the solar, and its magnetic field, it does all sorts of things. It protects the atmosphere from the solar wind, which is lots of particles being thrown off from the sun. and they get caught by the magnetic field, and they fly into the North and South Pole and make the Aurora Borealis, or the Northern Lights, which are quite pretty. So if the Earth's magnetic field flipped, it would probably almost disappear and start changing around. So we'd all get Northern Lights sort of at random. It would have some negative effects, though.
Would we all die?
Probably not, because we're still here, and humans have survived at least one, so probably wouldn't all die, which is always reassuring.
That's a relief, yeah.
And it might have effects on the climate, because it would heat up the top of the Earth's, top of the atmosphere, and it would do things like stopping radio communications.
I think we'd better stop you there.
You've not done anything to assuage my nightmares. Anyway, another thing that gives me nightmares is worrying about what we're doing to the climate and how our use of energy is affecting basically the climate and our needs. We're running out of fossil fuels at a desperate rate. And at the moment, the government is trying to work out if we should build more nuclear power stations. And there's a public consultation on this. And as part of this, I'm involved in writing a blog. This is an online diary for the Institute of Physics. And myself and a couple of other journalists, a woman called Gia Milinovich and a man called Caspar Henderson, over the next 10 weeks, we're going to be just looking at all the issues surrounding nuclear power and whether we should build nuclear reactors in the UK again. And we're sort of looking at it from all sorts of angles, thinking about nuclear waste, thinking about should we do it, what about the environment, what about the human impact, what about the politics of it and the financial aspects. So if you want to have a look at what we've got to say, and then also you can contribute, everyone's free to leave comments, get involved in it, it's a discussion. Go and have a look at www.potentialenergy.iop.org and get involved in the discussion. We're looking for people's views from all over the world, whether you're pro-nuclear, anti-nuclear, just not sure. Go and have a look and get involved.
It's people's big opportunity, isn't it? Because when it came round first time round, so few people knew anything about it anyway, except the scientists, that nobody actually had any dialogue. But now it's different.
Yeah, it's very important that people are informed about scientific issues, and it does revolve around science and also about politics and economics.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
Well, Dr. Chris isn't in the studio with us this evening, but has news of 3 new planets. Chris?
Well, HD 69830 might not be the most excitingly named star in our cosmic neighbourhood, but it's certainly got researchers buzzing in Switzerland, because Christoph Lovius and his colleagues at the Geneva Observatory have found in orbit 3 rocky planets about the size of Neptune. They're too small to see directly. In fact, it was the wobble they provoke in their home star that gave them away. But intriguingly, at least one of them is in the habitable zone, like the Earth. And that means it might also be a home to liquid water.
We have discovered a multi-planet system with 3 very low-mass planets, and it's the first such system with such low-mass planets. And of course, we are now beginning to discover planets that are only a few Earth masses in mass. So we are approaching planets of really small size, and it's become very interesting.
So you're into the kind of size which is almost Earth-like and therefore very similar in terms of their capacity to support life, perhaps?
Yes, for example. So we are not sure now what is their exact composition, but of course, if the mass is very low, then these planets are very likely to be mostly rocky, and in that case they would really look like the Earth.
Where are these planets?
So they are around a nearby star. This is a quite bright star that can be seen with the naked eye, and it's about 40 light years away from the Earth. And so these 3 planets are orbiting this star, which is quite like our Sun, a little bit less massive, a little bit cooler, but still much like our Sun.
And how did you actually make these observations?
We use dedicated instrumentation, which was developed with the goal of being able to discover extrasolar planets by measuring very precisely the radial velocity of the stars. All stars are moving across space, and each star has its own velocity in space. And so when observed from the Earth, we can measure the component of this velocity along our line of sight. So some stars are just receding from us and some stars are approaching. And on top of that, when they are orbited by planets, these planets will induce a little gravitational wobble on these stars, and they will make oscillations around their center of mass velocity, and we are able to measure these very tiny radial velocity changes.
So you saw this star literally wiggling a bit in space?
Yes.
But if it wiggles a bit, how do you know there's 3 planets then, if you can't see them?
The signal caused by a planet is expected to be like a sinusoid curve, and when we observed this star, we noticed that the radial velocity showed complicated changes that could not be only explained by one sine curve. And after accumulating enough measurements and trying orbital solutions, we found that the best solution was when we fitted 3 planets on these radial velocity curves.
And where are these planets in relation to the star itself?
The first one orbits with a period of 9 days. It is very, very close to the star, much closer to the star than, for example, Mercury in our own solar system. Then the second planet orbits in 30 days, which is a little bit further away. And most interesting is the third planet, which orbits in about 200 days, which becomes quite similar to the Earth. And so it's at about 60% of the Sun-Earth distance.
Is that within what we call the habitable zone for this particular star then?
Yes, for this particular star, it would be at the inner edge of the habitable zone, so that it means just at the border where the temperature is low enough for water to become liquid. And that's one of the definitions of the habitable zone.
Do you think there's water there, or do you not know anything about the composition of these particular planets?
At the moment, we have to be very careful. From the observations we have now published, we cannot say anything about the composition of these planets, but we have made some theoretical calculations that show these planets, at least the first 2, are mainly made of rocks, and the second one and the third one also contains a lot of ices. That means that there is a lot of water, but this water is not necessarily in the liquid form. It could be in ice.
I guess we'll just have to watch this space for more fertile findings from HD 69830 and its clutch of rocky worlds. That was Christophe Lovice from the Geneva Observatory describing the work he's published in this week's edition of Nature.
And Dr. Chris will be back with us in the studio next week.
The Naked Scientists, supported by the Wellcome Trust.
And you're listening to The Naked Scientist. Kat.
We are here today talking about music technology. What is the science of music and sound? How does it get to our ears, and how can we change it, manipulate it, and make entirely new sounds? And we have in the studio Dr. Hugh Hunt and Jez Wells, who are going to talk to us about this a bit later. And we've already had some emails in, some questions. We're going to come to those as well. But we've had a lovely little email here from Sagar. I'm not sure where he is. And he says he just stumbled on our Naked Scientist site. That's nakedscientist.com, where he was surfing the internet. He thinks it's great. And he's got an interest in biotechnology and physics, F-I-S-I-X. So probably he needs to work on his spelling a little bit more. And he also says that he's in love with me. So there you go.
Ooh.
But if you've got any more constructive things to say, then get calling in today to be on the show. 08459 25 2000. Email us, chris@nakedscientist.com. We want to hear from you.
Now, Science Update this week. We're going to take our weekly trip over the ocean for a science update from Chelsea Wald and Bob Hershen. This week, they're going to be looking at the king of all hormones, testosterone, including its potential use in stopping the progression of MS and how too much of it may lead to some birds to an early grave.
This week, for the Naked Scientists, we'll be talking about testosterone. Although it's present in both sexes, testosterone is commonly known as the male hormone. That's because males have more of it, and it strongly influences male sex traits and mating habits. Now, a study in birds shows that extra testosterone can give males a leg up in the mating game, at a big price.
Would you die younger for a better sex life? Well, that's what extra testosterone does for birds called dark-eyed juncos. North Dakota State University biologist Wendy Reed and her colleagues found that when young male juncos were treated with extra testosterone, they attracted older, more fertile females, had more extramarital sex, and fathered more offspring than untreated males. But Reed says that attracting more mates also seemed to attract more predators.
They also had lower immune function than control males, and so they paid a cost of that in actually lower survival rates.
What's more, their offspring were smaller and weaker than normal, and the testosterone-treated dads tended to skip out on their parenting duties. Reed says that factors like these may keep the junco population's natural testosterone levels in check.
And testosterone not only gives human males hairy chests, deep voices, and an insatiable appetite for sports, it may also protect them from multiple sclerosis. Men get the autoimmune disease less than women, and when they do, it's often when their testosterone levels have dropped with age. So a team from the University of California, Los Angeles had 10 men with MS rub a testosterone gel on their skin every day for a year. The team then tested their brain processing speed and memory. Neurologist Nancy Sykott says the result was an improvement on all counts.
And in general, people with MS, we would have expected to see a decline in those abilities because that's typically what happens. So it suggests that not only could they not get worse, but they might actually have some improvements.
If they can confirm this effect in larger studies, this treatment could be the first to protect MS patients from brain damage. It wouldn't be suitable for women because of the side effects, but the same team has found that the pregnancy hormone estriol might work for women.
Thanks, Chelsea. Well, you've heard of cyber gambling and cyber sex. Next week, we'll talk about a new project that will let anyone with an internet connection dissect fish.
Until then, I'm Chelsea Wald.
And I'm Bob Hirschon for AAAS, the Science Society. Back to you, Naked Scientists.
Thanks to Bob and Chelsea. And if you want to hear more from them, more of their science updates, pop along to their website, www.scienceupdate.com.
Baffled by biology? Yep. Foxed by physics?
Oh, yes.
To get your question answered, call the Naked Scientist now on 08459 25 2000 or email chris@nakedscientist.com.
Well, now we're off to Ely in Cambridgeshire to join Anna Lacey for this week's Kitchen Science. She's with Wendy, Sophie and Hannah, who are waiting to find out about harmonics and making music with nothing but a pink tube. Hello, Anna.
Hello and welcome to the King's School in Ely, where this week we're going to be doing some more sound and music experiments. So on this evening we've got our helper with us today, our science guru Wendy. What are you here to do today?
Well, we're going to be doing an experiment with quite a simple but rather strange looking musical instrument.
Yes, it does look very strange and very pink, I have to say. And we've also got our student helpers with us. Can you introduce yourselves? Name and ages, please.
Hi, I'm Sophie and I'm 13.
And yourself?
Hi, I'm Hannah and I'm 13.
And what's your favourite thing about science then, Sophie?
Probably the practical side of it.
And you, Hannah, are you a budding science Einstein?
I like doing the practicals as well.
So, Sophie, first of all, do you want to actually just describe exactly what Wendy's holding here?
It's quite long and it's a very nice bright pink. And it's got a lovely bumpy texture to it.
It kind of looks a bit like a corrugated elephant's trunk to me.
It does, actually.
I mean, would you go with that, Hannah?
Yeah, I think it does look like that.
And so, Wendy, what exactly do you want these girls to do with this strange pink pipe?
Well, if you take an ordinary pipe, this one is a bit strange, as you can see, and sort of spin it around your head, you wouldn't really expect anything much to happen. So maybe if we ask Sophie, first of all, just to give that a try, to take this pipe, which is a little bit unusual, and just spin it around, and we'll see what sort of result she gets for this experiment.
OK, so we're all just going to stand back in order to make sure nothing bad happens. And Sophie is standing there holding the pink pipe, ready to twirl it around her head like crazy. So, go, Sophie. Ooh, OK, so we're getting some kind of eerie noise. I mean, Sophie, what did it sound like to you?
I realised it stayed at the same note and it just sort of gave me the shivers, really.
Right, well, Sophie, I noticed when she was twirling that around her head, was doing it at the same kind of speed, and we had a note there. So what we're going to ask you to do is now try it at a different speed. So, I mean, Wendy, you're quite a pro at this. Do you want to just give it a go at a different speed?
Years of practice, OK. Let's see if we can get the note that Sophie just got. Which I think was that one. And if I go a little bit faster...
So, Hannah, what was the big change there? What did Wendy do differently?
As Wendy speeded up, it went higher. When she slowed down, it went lower.
Now, Wendy, why exactly was that?
Well, the main thing that's different about this tube to, say, a piece of hose pipe or something is these corrugations that you mentioned along the tube. So it's a very bumpy tube, and those bumps aren't just along the outside of the tube, they actually go into the inside as well. So if you feel inside, the inside's corrugated as well. So there's two things that need to happen to make this tube make a noise. And most people know that anything that makes a sound is happening because something is vibrating somewhere. So what happens is there's two parts, really. As I spin the tube around my head, like that, the one thing that you'll notice is that the long end furthest away from me, the floppy, the bit that's sort of hanging down, is spinning much faster than this end that I'm holding.
So there's lower pressure near the far end of the tube?
Yeah, because it's moving fast. So what you've got then is a pressure difference, and the air is moving through the tube. And with most musical instruments, you get air moving through the tube by perhaps blowing it. But this is a different way of getting the air moving, if you like. Then the second thing, as I said, the most important thing is these corrugations. Now, as the air's travelling through the pipe, it's getting to wider parts and narrower parts, wider parts and narrower parts, all the way along the tube. So effectively, the air's getting sort of jiggled about, and it's getting very turbulent. And it's this jiggling and turbulence that starts the vibration that gives us the sound.
So what's happening is, while you're twirling that around like a helicopter, there's a pressure difference from the end near your hand and the end at the far end of the tube, which pulls air through kind of like a wind tunnel. But then the air doesn't just move through slowly, but it actually gets jiggled about, and that makes a noise. So why does it change then when you do it at a different speed?
Well, there's a certain number of vibrations, if you like, that you can set up in this length of tube. So the speed that you're vibrating the air at affects how many waves you can fit in this length of tube. And if you've got that happening in air, what you hear is these specific different notes. You can't get every note of the scale. You can only get certain notes.
OK, so does this have anything to do with harmonics?
Yeah, that's what these basically are. We are listening to some harmonics of a pink tube instrument, and many musical instruments have this, and musicians would know these notes as called the harmonic series. And lots of people who play instruments have the ability to change the harmonics they hear by just tightening or changing the way their lips vibrate.
Wow, so musicians are actually performing proper sound science every time they pick up their instrument. Wow, that's just amazing, if you ask me. But something even more amazing than that, Wendy, you can actually play a tune on this amazing tube, can't you?
Yes, something to be very proud of, I think. After 7 years of practising, I've put together, there are 5 notes that I can get out of this tube, and if you put them together in a certain order, hopefully I can make a tune that some of the listeners might recognise.
Well, OK, for your listening pleasure, Wendy from Science Made Simple plays us a tune with a pink pipe. Can we have a round of applause, please, for Wendy?
I think I took out the light completely in that. But
yeah, this is where a low ceiling is not good. So can you just tell us, enlighten us exactly what the tune was?
Yeah, it was The Last Post, which you often hear played on a bugle, of course, on Remembrance Sunday.
That's absolutely wonderful. So what did you think of that, Sophie?
Excellent. I don't know how she does it.
And what did you think of the science behind all that?
I thought that was very interesting, how she can make a song out of just one pipe.
It's true. It's amazing. You heard it here first on The Naked Scientist in our Kitchen Science. Well, that's all for this week. Thanks very much to Wendy, Sophie and Hannah, and the King's School in Ely. We'll be back next week in another school in the Eastern Counties for some more kitchen science. Goodbye.
Thanks, Anna. Next week, Derek and Sheena will be in Essex making boats out of matchsticks to find out how surface tension works. If you're keen and want to be ready for next week, you'll need to find a few matches, a shallow tray or large dish filled with water, and some washing up liquid. Once you've found all that, just tune in next week and we'll tell you what you need to do.
Stripping down science.
Okay, let's do it.
The Naked Scientists.
This evening we've got Hugh Hunt from the engineering department in Cambridge with us, and he's now holding a knife, just a normal kitchen knife. So what are you going to do with that, Hugh?
Well, we've just heard from Ely about harmonics, which you can get from this tube. Well, actually, if you listen around pretty much anywhere, you can find harmonics all over the place. So I've got an ordinary eating knife. It's not one of those dangerous ones which you don't want to be holding by the blade. This is an ordinary knife, and if I tap it like this, I can get a nice note. I'm just holding it roughly halfway along. But if I hold it somewhere else, I can get a different note.
Yeah. Okay.
And so, depending on where you hold it, you get different notes. And if you hold it right at the end, you don't get...
So that's holding it right at the very tip of the blade.
Yeah, either end, you don't get any note at all. But it's quite interesting just to explore where you have to hold a fork to get these notes.
I see you've got a big aluminium tube behind you. Is that a bigger version of the same thing?
Well, yeah, it is. It's as ever. It's always much easier to demonstrate these things cleanly if you have somehow a contrived perfect experiment. So I've got a tube here which is about 6 foot long, a couple of metres.
It's like a scaffolding post, isn't it?
It isn't like a scaffolding post. It's hollow inside, so you can play it like a didgeridoo as well. But I won't do that now. And if I hold it at the end, it just goes thwack.
Like the lights.
It doesn't do anything. But if I hold it in special places, I can get really quite nice notes. I can get this one.
So you're holding it about halfway up, isn't it?
There's lots of different places. I've marked this tube with different coloured strips so I know exactly where to hold it. Now, this is getting the 5th harmonic. So it's starting from the very bottom, going up the harmonic series, and a little bit like that pipe we heard before with its harmonic series. This is the 5th one up. Then if I hold it somewhere different, I can get the 6th one up.
So it's a bit higher.
And then I can get the 7th one up if I go to... That's it.
That's a lot higher.
And I can go a bit down. I can get the 4th one, which is here.
Okay.
And I can get the 3rd one.
So what's actually happening to the tube when you hit it?
Well, the tube is vibrating. If you imagine that you got a long piece of spaghetti, not cooked spaghetti, uncooked spaghetti, and you could bend it. You could bend it as it were in the shape of the letter C. Well, you could imagine the cooked spaghetti, if it was floating around in space, could vibrate backwards and forwards like that letter C. But you could, if you used 3 fingers, bend it in the shape of the letter S, and it would vibrate backwards and forwards in the shape of the letter S. And then you could go one step further and bend it in the shape of a sort of a squiggly letter, well, like a number 3, but
with another bit.
Yeah, exactly. And then you can make it really serpentine and make it very wiggly. Well, it turns out that every time you introduce more bends, you have to. There's more energy in it, a higher energy, higher frequencies, and that's the same with light. You might know that the energy goes up with frequency.
So the pitch gets higher.
And the pitch gets
more
higher.
wobbles you have in the rod.
So that's right. So all I'm doing with these marks on my tube here is noticing that I can pick out these different harmonics.
So basically, where you're holding the rod can't be wobbling. So there must be
That's right. It's called a nodal point. And so, for instance, the 5th harmonic on this rod has got 6 nodal points, and the 6th harmonic has got 7 nodal points, and so on. It's like if you draw that wobble, a letter S has got 2 spots that go through, 3 spots that go through the middle, and a letter C has got 2 spots.
So you can do that for example, on a guitar, if you very gently put your finger against the very middle of the string.
Yes. So
is that the same principle? You get that very high pingy sound.
So if you're playing a stringed instrument, a guitar or a cello or a violin, you can play the note and then just touch it in the middle, and you'll get an octave higher. And if you touch it a third the way along, you get an octave and a half higher. And this is all this harmonic series. And the harmonic series goes like this. It starts here, and then it goes 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 here, and it goes here. And so that's why you heard the last post before. That was... It's just that harmonic series.
So what Wendy was doing with the tube was driving different ones of the harmonics at different times so you can make the tune.
And Hugh, interestingly enough, if you're going into a guitar shop to buy a new guitar, the first thing you do is test the harmonics, because that will tell you whether the bridge is true or not.
Absolutely right. And the harmonics are so wonderful that composers throughout the centuries have used them in all sorts of ways. And there's a wonderful bit in Brahms's First Symphony which goes like this. And that's all using harmonics, and it's played on the horns, and it's just magic.
Is this because it's very difficult to play anything other than the harmonic series on a horn? Or?
Well, yeah, but that's if you want to tell your kids to play any instrument, don't tell them to play the horn, because they're the ones that get all the blame when things don't go wrong in the concerts.
Well,
they fluff all the notes.
We've got a question for you here, Hugh, from Andy in North Carolina. If you take a 2-litre plastic soda bottle, it's in America, and blow across the lip, you get a very low note. If you squeeze the bottle and making it flat, you get a higher note. What's going on?
Oh, well, look, I have to tell you that I discovered this at a party when I was a teenager. It was a New Year's Eve party in Australia. It was a very hot night, and everyone was taking off their clothes and having great fun in the pool, and I was sitting in the corner experimenting with these plastic bottles. You know, this is but I've become a bit less geeky since then. I managed to find a bottle in a rubbish bin here, and so I can demonstrate this for you. So I've got a little plastic bottle, and I'm going to blow the note. Now, we all know that if I put a little bit of water in the bottle, we expect the note to go up. So, gluck, gluck, gluck. There we go. You heard that, so that's water. And here the note is higher, which is great. So I'll pour that water back into my container here and back to where we were. So the question is, if I squeeze the bottle like this and make it smaller, surely the note should also go up. But what happens is I get...
That's much lower.
Goes down.
And you think, crikey, that doesn't do what I expected to do.
Physics is wrong.
Physics is wrong. But now, the reason why it was very important back those many years ago on that hot, balmy night when everyone was taking off their clothes, that I was at a swimming pool, was because you can actually do a rather interesting experiment. If I take that bottle, which I've squeezed, and I lower it into the water. I've got a tub of water here, and I'm going to lower it into the water, and as I lower it in, I'm not squeezing the bottle at all anymore. It's squeezed, and I go into the water.
Goes up, doesn't it?
Goes up again. That's amazing.
So the question is, why is it when I lower it into the water, and it starts to give you a clue? And the answer is this, that when the bottle is perfectly round, then we know that round things are stiff and solid. That's why pressure vessels are round. That's in fact why a Coke bottle with pressure in it is round, because that's the strongest shape. But when you squeeze it, you make the sides flat, and that makes them weak. So actually, you can tell when you put your finger on the side of the bottle, you will actually be able to feel the flat bits are vibrating a lot. And that means that the bottle has an effective size which is bigger than it really is, because it's actually moving some of the space around it.
So it's actually got to move the bottle itself.
It's got to move the bottle itself.
Everything down.
Yeah, and now it's very interesting. You can do a similar sort of thing. Is if you take a bottle which isn't a round bottle, but it's a square bottle. So this is an unpressurized mineral water bottle, and it has a note. And even without doing anything to it at all, no squeezing or anything, I lower that into the water, and the note will go up. Even just because those square sides, and I'm not sure whether this
is
thing's...
stopping it from vibrating.
Hugh's having to...
Oh, I mean, my vessel's not big enough here. I can't... Anyway, you can try that for yourself. And it is absolutely amazing.
That's absolutely incredible. Do we have some questions on the phones, Mandy?
We have got David, who's given us a call from Ipswich, and we've been trying to get him back, but we can't, so we shall put the question for you, David. The question that he wants to know is, that he would like to know, could sound waves be heard on Mars? So basically, could they travel through the atmosphere all the way to Mars?
Well, I suppose there are two questions here. One is, if we were... had a very loud screaming baby on the Earth, could somebody on Mars, in theory, hear the baby screaming? Or would you need to have a special interplanetary baby monitor? And the answer is no, you wouldn't be able to hear the sound from Earth on Mars, because the space in between Earth and Mars is a vacuum. And there's a wonderful experiment you can do where you put an alarm clock under a bell jar, and you start the vacuum pump going, and you get all the air evacuated, and you can't hear the bell, even though the bell is still going. But then the question is, well, what if your baby was in the bedroom in your Mars planetary home? And would you be able to hear the baby crying from downstairs in your bedsit? And the answer would depend very much on the atmosphere on Mars. And my understanding is that there's not very much atmosphere.
I think it's about 1% of the atmosphere on Earth.
And so it's getting close to a vacuum. So there are two things. One is that the amount of energy that you can pump into the atmosphere is less, and also the speed of sound will be a lot faster, and so all sorts of things will be different. But of course, it's a bit of a funny question, because with 1% of the atmosphere, we wouldn't really be breathing the atmosphere, and so we'd probably do it all through microphones. But by then, we'd probably have invented communicating in the seventh dimension.
So the moral of this, if you've got a really loud baby, send it to Mars.
Send it to Mars.
Absolutely, right.
Oh, do you mean as in grandmas?
Send it to grandmas as well. Anyway, we're going to move on and have a chat to Jez now, who's from the Department of Electronics at the University of York. And Jez and his colleagues up there are doing some really fascinating work into how we can recreate sounds that basically don't really exist anymore. Jez, tell us about it.
Well, there are two ways that you can think about sound. You can either think about sound as it arrives at the ear, or you can think about sound as it's being made as an instrument. And we look at both aspects. We look at physical modelling and spectral modelling, as it's called, of sound. So spectral modelling is all about sound, the nature of sound as it enters the ear, and physical modelling is all about the nature of sound as it is created at an instrument. So some of the things that Hugh's just been talking about, if you think about a guitar string, when we are trying to create a physical model of a guitar string, we're interested in how long it's going to take a sound wave to travel down the string up to the bridge of the guitar, and then what's going to happen to that sound wave when it gets to the bridge. Some of it's going to be reflected back down the string, some of it is going to be passed on to the body of the guitar. And so when we're building physical models of instruments, what we're interested in doing is working out how all of these different physical components of an instrument actually fit together and interact to create sound. And then once we've created a physical model, what we then have to do is excite it. And that means usually plucking it if it's a stringed instrument, or blowing it if it's a bottle or a flute or something like that. And then what we're interested in doing is hearing it. So we, as well as exciting it, we need to put a microphone somewhere around our physical model. This is something which a computer is effectively imagining. And when we put that microphone near to it, we might put it near to a certain part of the instrument to get a particular kind of sound, or to another part of the instrument to get a particular sound. This is something that recording engineers do all the time. When you're miking up a guitar or a harp or something like that, you're always interested in getting the best sound. Is there too much noise from the player's fingers and that kind of thing? What we can do is you can take a physical model, and that's a one-dimensional physical model where we're interested in waves propagating up and down a string. We can look at that in 2 dimensions. We can create a mesh, if you like.
Are these all computer models?
These are all computer models, yes. So they're all imagined.
Imaginary music.
Absolutely. They're a bit easier to get in on the train or in the car than Hugh's pipe, I should imagine. But hopefully they're just as much fun to play. And another important aspect of physical models is how we can actually interact with them, because having these things trapped inside a laptop isn't much good. A QWERTY keyboard isn't much fun to play. So interfaces and how we analyse human gesture and turn that into musical gestures is another very important part of physical modelling. But the models themselves, yes, they actually reside inside the imagination of the modeller and inside the memory and the processor of the computer.
So let's actually, you've brought some examples of some of your work today. So
yeah, I mean, this is work that's been done by one of my colleagues, Dr. Damien Murphy, who has been working on 3-dimensional physical models. Now, the great thing about 3-dimensional physical models is we can actually start to imagine spaces as opposed to 1-dimensional things such as the length of string, or a 2-dimensional thing such as the skin of a drum. Now, the great thing about being able to imagine spaces is that if you're an architect, you haven't got to wait until the final bit of carpet is rolled out in your auditorium until you find out whether it sounds any good or not. Now, rather than having to build a small model, which is what used to happen, they would build a small model and actually take physical measurements from this tiny model of the auditorium. Now we can actually put the architectural design into a computer, and it imagines that it is air sitting inside that space. So as you make a sound, normally we're interested in an impulsive sound, something like the clapping of hands, and quite often we start off with a gun sound, something like that, and we're interested in how the building responds. Now, what happens when a gun is fired is that sound waves begin to move through the air particles, which is one of the reasons why in a vacuum we can't have sound. It has to have a medium to travel through. But then it reaches certain objects, people, walls, that kind of thing, and we're interested in what happens. Some of it will be absorbed, some of it will be reflected back, and that's dependent on the nature of the sound, the frequency of the sound, and so on. And so what we've got in this three-dimensional modelling is we can say, OK, even though this building doesn't exist, what would it sound like? Which is quite handy for buildings which have been destroyed or by fire or by warfare, and for buildings which haven't yet been made.
So we've got an example here, which is, I gather, the sound of Coventry Cathedral before it got blown up.
That's the old Coventry Cathedral, yes. There's a fully functioning new Coventry Cathedral, but the old Coventry Cathedral was destroyed during the Second World War. So what you'll hear, I think the first thing you're going to hear is the impulse.
So this
Angel voices ever singing round thy throne of night.
Lovely.
That wasn't an impulse, as you probably gathered. That was the sound of a chorister singing a hymn. That was recorded in an anechoic chamber, which means that that's a room without any echo at all. I hope what we'll hear next is the sound of what sounds like a gun being fired in a large reverberant space.
Let's try this. Ooh.
Yes, that's the impulse. OK, so now what we're going to do is we're actually going to, by a process known as convolution, we're actually going to combine the sound of the chorister with the sound of Coventry Cathedral. So this is what that chorister might have sounded like had they been able to sing in Coventry Cathedral before it was destroyed.
Angel voices ever singing round thy throne of night.
Oh, lovely. Not the sound of a chorister being shot, which is what I was worried it would be. So we've got some other sounds here. So you're also working on how to combine the noises of instruments to make entirely new sounds.
Well, having just talked about physical modelling, I'll explain a little bit about spectral modelling, which is where we're interested in the makeup of sounds. Hugh was playing different harmonics from a pipe. And what happens if you combine those harmonics is you get the sound of an instrument. For example, the reason that we can tell the difference between a trumpet and a violin playing the same note for the same duration at the same loudness is because the relationship between the harmonics, the loudness of individual harmonics, is different. And so with spectral modelling, what we're able to do is to break sounds down into these fundamental ingredients, if you like. It's a little bit like taking a cup of coffee and being able to work out how many sugars it's got in it, how much milk it's got in it, and what the coffee beans were, because then you can begin to say, well, what would happen if I added 10 sugars, or what would happen if I took all the milk out and put cream in instead? So one of the things that I'm interested in doing is creating sound hybrids, and one of the things that I've produced is something called a flowbow. Now, a flowbow is what would happen if a flute and an oboe were to get together and have baby instruments, I guess. The idea here is not to combine the two sounds in such a way that it sounds like two instruments being played, but somehow they're being fused together. And so really, in physical terms, because we can think of spectral models in physical modelling terms as well, what we're doing is we're taking the excitation part of the oboe, which is the reed that vibrates, and we are imposing it on the resonant structure of the flute. We've also got some breathiness of the flute thrown in for good measure as well.
Right, let's hear this. So we've got the flute. Beautiful. And now we've got an oboe. Which, in my opinion, sounds a bit like a duck dying. But now, hopefully something more beautiful. Here is the flowbow we present. You can really hear hear the two different characteristics. It's intriguing.
Well, that's the idea. I mean, a lot of people expect music technology to be about amazing swooshes and amazing synthetic zap sounds and this kind of thing. But actually, I think music technology hopefully is now moving into an era where, sure, those kind of special effects can still be had, but we can move into creating sounds which are much more what I would call acoustically plausible, that sound like they could have been made by a real physical object. It's slightly unflattering having it in an anechoic chamber like that. It's great for us to actually analyse sound, but it's not so great. Generally, if ever you're going to make a recording, you'd put it in a nice auditorium or a cathedral, maybe.
And the final example that you've brought for us is something that really doesn't exist anymore, the sound of castrati. Now, how did you make this?
Well, this was for a programme which is going to be on BBC4 sometime this summer. It's a series about the 18th century, and they wanted to make a programme about castrati. Tell us briefly what castrati are. Castrati are boys who had exceptionally good voices would have been selected for castration. It was more of a snip rather than a hack, although I'm sure that wasn't much consolation. It's not quite as brutal an operation as some people have thought that it might have been. However, the reason that was done was to preserve their vocal folds or vocal cords as they're commonly known. That would prevent the vocal cords actually thickening and elongating during adolescence. But the body itself would continue to grow, and the mind would continue to develop, and all those years of training would pay off. And so what you would end up with was a man with a large vocal tract and a huge power supply, a big pair of lungs, in control of a pre-adolescent's vocal folds.
So let's have a listen to this. So we have first a sample of a tenor, so this is a male voice.
Yes, this is the sound of a tenor singing a Handel aria which was actually written for castrati.
Ombra mai fu.
Lovely. And now we have the sound of a treble.
Treble singing this. Now the treble is singing it an octave higher, and the idea is that we really want the resonant structure. We want the lungs and the vocal tract of the guy we just heard, but we want the vocal cords, the excitation of the guy we're about to hear.
And now we hear them both together. Incredible.
It's still work in progress. You can hear there are a few wobbles there. And one of the difficulties that we're having is that a boy's voice tends to be very breathy because they don't have the same kind of control as an adult singer, and so we need to find ways of removing that breathiness. But the final version should be aired sometime over the summer, I think.
Oh, that'd be fantastic.
OK, now, Hugh, you've got one more demo for us with a teacup, I believe.
Oh.
A mug.
A coffee cup. A mug.
I think this is brilliant.
Oh, sorry, just moving that around a bit. There we go.
People talking about sound having problems with the mics.
Yeah, there we go. Now, I've got a regular mug here. It doesn't have any logo on it. What's interesting is that if I get a teaspoon and just tap on the rim...
So you're just tipping straight opposite the...
Imagine like, you stir it, and then you just stirred your sugar in, and then you just want to tap the rim to get the drip off the end of the spoon, which is what we all do. Now, what you want to do is try this. Try tapping somewhere, and then try tapping somewhere else. And what you should find is that the note depends on where you tap it. So if I tap near the handle, I get a low note.
Now about 45
degrees around, I get a higher note, and then at 90 degrees around, back to low. 45 degrees, another 45 degrees high, and then opposite the handle, low.
So what's going on here, Hugh?
Well, if you take your mug, and if you put water in it, I'm just filling it up 3/4 of the way full of water, the note's gone down. So what that tells us is that if you add weight, if you add mass, then notes will come down. Just think of a mass vibrating on a rubber band. If it's heavy, it'll vibrate slowly. If it's light, it'll vibrate fast. Well, what's happening is that the way that the cup is vibrating is a bit like, imagine you squeezed it to make it oval shaped. Well, you can't really see that it's going oval shaped, but if it was a plastic cup, you could see when you squeeze it would go oval shape. But when you're hitting it, you're actually making it vibrate in an oval shape. And if you hit it opposite the handle, let's say, then that oval shape makes the handle move.
So it's going from sort of oval shape
one way to oval shape the other way. So yeah, imagine you take your cup and sort of wobble it oval one way, oval the other. So
yeah,
okay. But if I hit 45 degrees around from the handle, then do the same thing with the oval shape. The handle doesn't move as much because the handle is at that point, which is called the nodal point, which is the intersection of the two ovals at right angles to each other.
So it's not wobbling.
So it's not wobbling. So that means that the mug appears to be less heavy for the 45 degrees around. Therefore, the note's higher. So that's the less heavy, heavier.
So it's less heavy, so it can move faster, so it's higher.
That's it.
Got a question.
More questions, yeah.
Got a question for you from Steph on the email. My question is, when I play my flute, sometimes it gets a really screechy noise. What is it? It only happens when I play medium E natural.
Oh, well, that's... instruments are quirky things. It's a bit like cars. You know, you might be driving along, and when you go at 57.5 miles an hour, the steering wheel starts to wobble. There's just a particular characteristic of your car. Some things you can fix and other things you can't. Some of you who play cellos or stringed instruments might know about the wolf note. There's a certain note which just does funny things. And it could be that it's an interaction between the acoustic mode, the note you're playing, which is all to do with the air, and the actual structure of the flute, the metal that the flute's made of. And that's very important. For instance, you can think of a saxophone and a clarinet. Clarinet's made of wood and the saxophone's made of metal. And that's essentially what makes the two instruments really sound quite different. And so there is an interaction between the sound, the air, and the metal. And, you know, maybe that's why you pay your extra £500 for an ultra-good flute. And I think Stradivarius might have something to say about this. Not that he made flutes.
Laying the facts bare, the Naked Scientists.
We've had a question in from John, who's in upstate New York, so over in the States. And he says, quite an odd question, is white noise something to do with gravity or the Big Bang? Now, we're wondering if he actually means the Big Bang here, or if you've got some kind of white noise played in the style of Hey Big Spender. What's white noise?
Well, white noise...
what's the sound of the Big Bang?
Well, if I play a nice pure tone like this one, then that's got a particular frequency. But if I were to play all notes together, then that starts to be what we might call noise. Well, let's imagine that you played every single tone you could possibly imagine, not just the white and black notes on the piano, but also the notes in between. Well, in acoustics, we would call that white noise. Well, it's not just sound where you find vibration. You find vibration and waves on the surface of the water. You'll find vibration, actually light is a wave. You'll find waves in Slinky Springs. You'll find waves all over the place. Well, you might have heard of things like the cosmic background radiation or things like this. Well, actually, these are all electromagnetic waves of various kinds. And waves, light, can be just as much white noise as anything. So the reason it's called white noise is we know that white light is made up of all the colours of the rainbow. Lots of all frequencies all at once. So white noise is taken from white light. And yes, when there was the Big Bang, yes, all sorts of frequencies were emitted.
But I think with the Big Bang, there's a peak frequency, and so I can't remember what it is at the moment, but there is one peak frequency, so it's not all the frequencies at once, so it probably isn't really white noise.
Yeah, so if you fire that gun off in Coventry Cathedral and manage to miss one of the trebles, then you get a response which actually the gunfire does contain all frequencies equally, but the Coventry Cathedral will respond at particular frequencies is what makes it Coventry Cathedral. Likewise, the universe responded to the impulse of the Big Bang in a certain way, and we're left with what we've got.
Wasn't there some research a little while ago? I think the universe vibrates at, is it a low B flat?
Oh, yes. Well, that's right. Well, Carolyn Crawford, who's in the astronomy department here, and published a paper on this, and yes, it's several, I think it was 16 octaves below the bottom of the piano. And essentially that means that this galaxy somewhere way beyond Mars anyway, is vibrating, is pulsating. You know, imagine sort of breathing in and out. And it's pulsating at, well, what's 2 to the minus 16, but, very slowly anyway.
Tom in Essex has given us a call. Why do instruments from different countries not go well together? So I guess we're talking about guitars and sitars and all this sort of thing. Jez?
One of the reasons is that not all instruments are harmonic. If you were to take an example of, say, the Javanese gamelan or the Balinese gamelan, they use a lot of metallophones. And because they are metal bars, they don't actually have strictly harmonics. In fact, they're what we call partials, which means that rather than having a frequency at which they vibrate and then having harmonics above that at 1, 2, 3, 4 times, the modes of vibration, as we call them, they are no longer integer multiples, so they might be 1.54, 1.76. Hence, they make a wonderfully rich sound. But when we play them with other instruments, which are harmonics, the harmonics and the partials don't coincide with each other, and that causes a very confusing pattern of vibration inside the cochlea of the inner ear. And it's this which leads to problems with tuning between those two different instruments. So they're incompatible in terms of their harmonic structure and partial makeup.
We've got a really, really quick question here, and we have from Susie in Norwich. She says, what is ultrasound? Is it actually sound?
Yeah, ultrasound is sound, but it's so high a frequency that it's right, it's beyond, you can't hear it. And the frequency is so high, the wavelength's so small, but it is sound, you just can't hear it.
Definitely. Well, that was absolutely fascinating. And if you want to find out more sounds, you can listen again to our podcast, www.nakedscientist.com, and listen to the whole sound of this beautiful show again. Next week on The Naked Scientist, we'll be answering all your burning science and technology questions. Start emailing in now, chris@nakedscientist.com. And if you want to have a kitchen go at our kitchen science next week, then you need to get hold of some matchsticks, a shallow tray or dish, and some washing up liquid. So now all I have to do is say thank you so much to our wonderful guests, Hugh Hunt from Cambridge and Jez Wells from York, to Mandy Morton, the desktop extraordinaire, to Dave and me, I'm Dr. Kat, and also to our backroom team, Anna, Petra and Holly. So thanks very much.
But I haven't quite finished yet, Kat, because we've been talking about music for the whole show and all the different aspects of it. But a little bird tells me that when you're doing this, you are playing your own harp. Here is Dr. Kat to play us out.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.